At the top of the electron microscope is the electron gun. As we've discussed, it has a filament, and then what's often called the Wiener cylinder, and then an accelerator stack to accelerate the electrons as they come out and head down the column. And this is called the electron gun. Next we have the first lens system, which is called the condenser lens system, complete with a set of deflectors and lenses. Usually there's two, called C1 and C2, stigmators, and an aperture. The purpose of the condenser lens is to take the electrons coming out of the gun and focus and direct them onto the sample. So here I've drawn the sample coming in on what this looks like a spatula. Here's the sample, and the sample resides within the next lens system, which is the objective lens system. And the objective lens system has a pair of deflectors, the lens, here the objective lens, stigmators, and an aperture. The objective lens system produces a magnified image of the sample, and that magnified image is further magnified by the third lens system, which is called the projector lens system. It again has deflectors, and then usually a number of lenses. Here I've drawn three. The first two are often called intermediate lenses, and the last one would be called the projector lens. And it has a stigmator and again an aperture. Finally, the magnified image is sent through a final pair of deflectors onto some kind of detector. It may be a viewing screen or a piece of film or a camera or whatnot. And the idea of having so many lenses is that the electron microscope is a compound microscope, meaning that given an object, the first lens might produce a first real image of that object at perhaps 100 times magnification. And then the next lens system takes the first real image and further magnifies it into a second real image. And if the intermediate lens has a magnification factor of, say, 20, the second real image is now magnified by a factor of 2,000. Then another lens system, the projector lens system, can take that second real image and produce a third or final real image. And if the projector lens system also has a magnification factor of 100, then you can get final images with magnifications in the hundreds of thousands. In fact, most electron microscopes can deliver images at 1 to 5 million times magnification. Now the planes upon which these images exist, here, 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 and here where the original object is, are called conjugate planes, because the same wave function exists here and also here, and it is an image of the object that exists here, except that in each case it's magnified to a different factor, and we call those planes conjugate. Now returning to the full schematic of the column, we see that each lens system has each of the four elements of deflectors, a lens, a stigmator, and an aperture. In the case of the condenser lens system, the deflectors are called gun deflectors because their job is to take whatever electrons are coming out of the electron gun and shift them and change their angle so that they will come straight down the optical axis of the two condenser lenses. And this stigmator is called the condenser stigmator, and the aperture is called the condenser aperture. In the objective lens system, the deflectors are called beam deflectors because they're deflecting the beam that is being directed onto the sample. And then you have the objective lens, objective stigmator, and objective aperture. In the projector lens system, the deflectors are called image deflectors because they receive the first image that's formed by the objective lens system, and they move that image so that it passes directly down the center of the optical axis of the intermediate lenses. The stigmator, for reasons that we won't cover, is called the diffraction stigmator, and the aperture here is called the selected area aperture. Finally, the last set of deflectors are called projector deflectors, and they deflect the image onto whichever detector that you're using at the time, for instance, a viewing screen. These are the names of the knobs and the currents that you can control. Here, I've added the names of the parameters and the knobs that you get to change on the electron microscope. The first thing you can control is the current passing through the filament, which also controls how hot it gets. And that knob is usually called filament, or that parameter in the software is often called filament. Next, you can control the voltage difference between the Wiener cylinder and the filament. And this is sometimes called bias, or sometimes it's called emission. And it controls generally what percent of the electrons that are coming out of this tip are passed through here towards the accelerator stack. Next, in the accelerator stack, you control the voltage drop across the stack, and this is often called the high tension. Following the gun deflectors, the first condenser lens takes the electron beam that emerges from the accelerator stack and has perhaps been redirected by the gun deflectors. And the first condenser lens focuses it into a first spot. And so to control the current in that C1 condenser lens, the knob is called spot size. And perhaps counterintuitively, high spot sizes correspond to a small spot, which is going to be more coherent because some of the electrons that are most divergent won't actually be focused into that small spot. On the other hand, a low spot size corresponds to a larger spot that has more electrons in it, and it's brighter, but it's going to be less coherent. The next condenser lens is called C2, and it takes that first spot as the electrons emerge from that first spot, and its job is to focus these electrons onto a particular position on the sample. Now, I drew it first like this, where all the electrons would appear to hit exactly the same spot on the specimen. But in fact, usually you don't want to focus your beam and so it hits in exactly the same spot on the specimen. Instead, you want to spread it out a little bit and illuminate a region of the sample big enough to fill your image. More typically, what's done is to set the current in the C2 lens so that there is what's called a crossover point above the sample. So this focal point is called a crossover position. And that's placed above the sample. And as you strengthen the C2 lens, that crossover point rises in the microscope, and you see the region of your sample that's being illuminated gets larger and larger. On the other hand, if you decrease the strength of the C2 lens, then the crossover point will drop in the microscope until ultimately it could be focused right on your sample and you see the minimum size spot that you can create. Because of this, the current in the C2 lens, the knob there, is called intensity because it dramatically affects the intensity of the beam that you see on the sample. When you focus the spot to a small spot, it's very bright. When you spread it out into a large area, it looks very dim. And so they've named that knob intensity. Unsurprisingly, to control the stigmation of the condenser stigmator, that knob is called condenser stigmatism. Of the condenser aperture, you can control the size of that aperture, and you have to center it before you can take good pictures. Next, we come to the beam deflectors. And in analogy to gun shift and tilt, here the knobs that control the currents in the beam deflectors are called beam shift and tilt. The specimen is held by a specimen holder, and we'll talk more about how that's inserted and how its position is controlled. But for now, let's just note that what you get to control is the position of the specimen both its height in the microscope up or down, and that's called the Z height, and also the tilt. These specimen holders allow you to rotate the sample back and forth. And so you can control the tilt and also its position within the microscope, up and down, and left and right, and in and out. Next, the current in the objective lens is called focus. So to change that, you have to turn the focus knob. And it controls, of course, as scattering emerges out of the sample, the objective lens focuses that to a point coincident with the objective aperture. And depending on the current in the objective lens, that point can be drawn up or down as necessary. And we'll talk more about why you would defocus the microscope or keep it closer to focus. It's very important for image formation. Again, unsurprisingly, the stigmation applied by the objective stigmator is controlled by the knob's objective stigmatism. And in the objective aperture, you control the size of the aperture and its centering. Next, for the image deflectors, the knobs that control those currents are called image shift and tilt. The currents in the intermediate lenses are controlled together by the knob called magnification. Now it's possible to set your microscope to give you independent control of each of these lens currents. By the way, these lenses are called intermediate number 1, intermediate number 2. There can be more, and then usually the projector lens is the last one. And so you can set the microscope to give you free control of these currents. But to simplify the situation, the microscope designers will have picked a set of magnifications, major step sizes, for instance, 5,000 times magnification, or maybe 32,000 times magnification, 64,000 times magnification, perhaps 202,000 times magnification. They've picked a set of magnifications and chosen currents for each of the lenses so that together they will produce that total magnification. So all you have to do is change the magnification knob to choose between these major step sizes, and the currents in all the lenses will change. Having a number of preset magnifications also allows the microscope manufacturers to choose a set of lens currents in the different lenses that will minimize the net rotation of the image as it comes through the column. Remember that electron microscope lenses, as they form an image, it rotates as it moves through the lens. And so it's advantageous to be able to move up and down through magnification without having the image rotate wildly. And so by having these preset magnifications, all of the lens currents can be chosen so that each time the image is not rotating much from one setting to another. Now, the first time you start doing this, you'll notice that as you change the magnification, there are several regimes of magnification. The lowest regime is called low magnifications, and the next one is usually called M, and then the higher magnifications are called SA, the SA range. And what's happening here is that if you're in the SA range, all three of these lenses are on, and their currents give you whichever magnification you're seeking. But if you want to drop to very low magnifications, for instance, the M range usually is around 2,000 times magnification, it turns out that the best way to get that kind of magnification is to turn off one of the lenses. So perhaps in the M mode, it'll actually turn off intermediate lens number 1. And so only intermediate lens 2 and the projector will be on. Likewise, if you want to go to really low magnifications, like for instance 500 times mag, the best settings may be to turn off both intermediate 1 and intermediate 2 and leave on only the projector lens. Now when you go through these ranges, you need to be aware that switching ranges can dramatically affect the microscope, because turning on or off a lens can change significantly how much heat is being produced by that lens. So for instance, if you're working in SA mode and your microscope is well aligned, and then you drop to LM, two of the lenses will turn off. They stop producing heat. The cooling water is still passing through the microscope. And so the whole microscope may cool down a little bit. And this will change the resistivities of all of the coils and change the magnetic field somewhat. So you'll find that your microscope is more stable if you can stay in the same range. Finally, for the diffraction stigmator, obviously you get to control the stigmatism there and the size and the position of the selected area aperture. For the projector deflectors, usually you're just given choices of diverting the image either to a TV camera, say that might be positioned here at the side, so you can choose the position that will divert the image to the TV, or you can leave the image going straight forward onto the viewing screen, or perhaps cameras that reside below the viewing screen. Now, as you start to work with an electron microscopy group, you'll hear people talk about aligning the microscope. We're always talking about alignment. And what it means to align a microscope is that when they build the microscope and assemble these lenses and all of the components on top of each other, they try as hard as they can to mount them in exactly along one axis. But when you're talking about distances of nanometers, it's impossible to have each element perfectly physically aligned. And that, of course, is one of the reasons why you have deflectors. So for each imaging condition that we'll use in the microscope, we can determine what deflector settings are needed to take the emission coming from the filament and shift it and tilt it so that it'll be coming right down the optical axis of the first set of lenses. And then again, we may need to shift it and tilt it so that it comes right through the optical axis of the objective lens. And finally, we may need to shift and tilt it again so that it comes right down the optical axis of the projector lenses. So what it means to align the microscope is to find those deflector settings in all these deflectors that will produce a well-formed image that goes through nearly the optical axis of all the lens systems. And once those deflector settings are found, they can be stored. Then to align the microscope, one would change the magnification to a different magnification and retune it and find those deflector settings that achieved this same result. And those would be stored for that particular magnification, and so on through all the magnifications that might be used. Now, as the microscope is used each day, those alignment parameters can vary for a number of reasons. One is, for instance, that the shape of the tip can change over time. Exactly which parts of that sharp tip the electrons are coming out of can change subtly the direction and the number of electrons coming from each position. And when that changes, then you may need different gun deflector settings. In addition, there can be slow changes in temperature in the room or perhaps in the cooling water. And if the temperature changes in any position in the microscope, then resistivities of wires change, electric fields, magnetic fields change, and it could need different alignment settings. One of the alignments is called pivot points, and each set of deflectors has a pivot point alignment. What the pivot point alignment is about, I'm going to draw another set of deflectors over here. And remember that the purpose of a deflector set is to be able to take radiation coming, a beam of radiation coming in any particular direction, and move it and then untilt it so that it would come down right through the optical axis of some lens below it. Now, in addition, there are times when we want to deliberately tilt the incoming radiation. So we might want to deliberately set the tilt over here or over here. Or we may want to shift the illumination to a different position and then have it come straight down. And so deflectors allow you to shift and tilt the incoming beam. But of course, a shift and a tilt require changes in the currents of both deflector sets. And ideally, we would be able to ask for a specific shift of the beam, for instance, from, say, here to over here, and have that shift without any tilt being involved. Or vice versa, we might like to be able to tilt the beam from straight down to coming at an angle without any shift along with it. And so what the pivot point alignment does is sets various parameters that convert your command to deliver a shift or a tilt into changes in the currents in these coils. And the pivot points allow it to deliver a shift without any tilt and a tilt without any shift. And so that's called aligning the pivot points. Now, alignment is different than calibration. There's a number of software packages today that allow microscopes to take images automatically and then move on to another specimen and focus and take another picture and then move on and take another picture, all without any user needing to be there. These packages require that certain commands in the microscope be calibrated. And what this means, for instance, is if the software asks for a beam shift of, say, 100 nanometers to the left, it needs to know, if it asks the microscope for a 100 nanometer shift, how much shift is actually applied. It may be less, it may be a little bit more. And so most of these software packages, you'll need to go through calibration procedures where you ask the microscope for a certain shift or tilt and then measure what the microscope actually delivers, and you can calibrate the response that way. Now, in all this work of alignment and calibration, an important issue that comes up is hysteresis. What hysteresis is, if we were to plot the magnetic field produced by a lens as a function of the current going through that lens, if we were to start at low current and a low magnetic field, we would see that as we increased the current, the magnetic field would increase with it. However, if from that condition we were to decrease the current, we would find that the magnetic field didn't follow exactly the same curve on its way up. So moving in this direction, it would follow this curve. But if we move the current back, it follows this curve. And so it isn't the case that for a specific current, you have one and only one magnetic field that's produced. You might get a magnetic field of this on your way up, but if you're reducing the strength of the lens, you might get a magnetic field of that, which is quite different. And this is called hysteresis. And it has to do with the memory of a metal of what was the previous magnetic field. If the metal is highly magnetized and then the current is reduced, some of the ordering that produces the magnetic field will persist. Now, what this means is that if you're using the microscope and you're using it at, let's say, 5,000 times magnification, and then you move to 18,000 times magnification and set up your conditions just right for imaging, but then you move higher to, say, 32,000 times magnification and set up the imaging conditions in that situation, and then you move back down to 18,000, you might find that your conditions aren't right anymore. And that's because the state of the microscope depends not only on the exact currents in all the coils at that moment, but also what the currents were in the states preceding arriving to that situation. And because of this, there's a button on the microscope which is called normalize. And what normalize does, when you hit that button, it will take many of the currents in the microscope, and it will run the current up to a high value, then back down to a low value, and then back up to whatever situation you were in when you hit the button normalize. And this is supposed to standardize the result so that anytime you go to a situation and you hit normalize, it should recover to what you expect.